3.03, we're now going to use the knowledge we've learned about electricity and apply it to circuits. So this is when a power that was generated from the power lines goes amok, and this is when the current is not properly contained. So it's really important to understand that the power of electric current and how to channel this powerful current to make electricity useful for us. So let's say we're standing on the bank of a river and we want to get to the other side, but the river is too wide to jump and there's no bridge, so you can't get across the river. Just as you cannot get across the huge river without a bridge, electrons cannot travel across from one point to the other without a path to travel on. Well, that makes sense, right? This path is called a circuit, and it's simply the path which electrons can travel. When electrons travel along a circuit, a current flows in the circuit. The circuit must be complete in order for the current to flow. Every complete circuit contains a voltage source, like a battery, an unbroken path, which the electrons can move through, and most of those times the path is of wire because wire is a really great conductor, so the electrons flow easily through there. And they also have some kind of device electric current to do work, otherwise there would be no point in just flowing electricity for no reason. So let's see, what does a complete circuit look like? This is an example. Here's our voltage piece, our path, and the area to do work. So it's lighting up a light bulb. An incomplete current. We only have path from one end of the voltage to the area to do work. And it doesn't matter which end, but it must, now see both ends have two wires, but that's not going to work. It must go from the negative to the positive. It's the only way it'll work is from the negative to the positive. All right, let's try. And I want you to pause real quick, and I want you to find some switches in your home. How many different examples of switches do you have in your home? We have a lot of two-way switches. We have the on and off, like the light bulbs. I know my coffee pot has a switch on it. The baby monitor has a switch on it. The TV on-off switch. Think about all the switches you have in your home. When we have them on, the current easily flows through because the circuit is now complete. But when they're turned off, it breaks the circuit, so it cannot allow the current to flow through. And do you think there are any other ways other than the two-way switch? Let's find out some more. The circuit diagrams. We have battery, which is what does work for us. I'm sorry, light bulb. The battery is what provides the voltage. The switch turns on or off the volt, whether it releases it or not. A buzzer, again, that can do the work. A motor can do work. Resistor, that can slow down the flow of electrons, so it makes it slow through. And voltmeters measure the voltage, and ammeters measure the amperes. Okay, so we've got this diagram here and what it should look like. So which symbols are being used here? Let's click the connectors to turn the circuit on and off. Once the circuit is connected, notice the letter I with the arrows pointing the direction the current is flowing. The letter I represents the electric current, or the rate of flow. Okay, see, it goes from the negative into the positive. So the R would be our resistor. It's slowing it down. The A is where we've got the work that's being done. K, that would be our path that we're following through. And then E is the electricity. We have our positive and negative here. Let's talk about resistors. Every component in a circuit slows the flow of electron through the circuit to some degree. The resistance of a circuit component is a measure of how much the component slows the flow of electrons. Remember, we talked earlier that the resistors are going to slow it down. It's really good for insulators. It kind of slows the flow down a little bit so it's not so quick, so fast. It's really similar to friction. We learned about friction back in Module 1. Friction slows the motion of an object, and resistance slows the flow of electrons. And they both convert kinetic energy into heat. We often typically ignore the resistor because it's such a small part of the component, and so we kind of ignore that in the wires when we determine the overall resistance of a circuit. It does affect the amount of amperage or current in the circuit. As resistance increases, the current decreases. Of course, right? If we're going to slow or stop the flow of electrons, then that would make sense for the voltage or for the amperage to decrease. And the voltage will stay the same because it's still backed up there. It's still going to release how much is allowed. However, if voltage increases and resistance stays the same, the current will increase. And this is the physical law called Ohm's law, and that describes the relationship between current, voltage, and resistance. It states that amperage, remember that's I, in the circuit is equal to the voltage in the circuit divided by the resistance. So this can be I amperage equals voltage divided by resistance. Typically, you'll see it more like V equals I times R or V equals IR. So you have the division part there. You just it's very important to consider voltage, current, resistance before building a circuit. In Europe, the electrical outlets provide a voltage of 220 volts. The US provide 110 volts. So we cannot plug our computer into an electrical outlet in Europe because the resistance in our computer circuits won't change, but the voltage now doubles. And what's going to happen when our voltage doubles? We're going to fry our computer. So we would have to have a special converter that would only allow 110 volts to our computers in Europe. We have different types of circuits. We have series and parallel. Series is just like we are seeing here. It's just a square. And that's what we've been looking at so far, is just series circuits. Electrons travel along one path, only one path. If that path is broken, the current stops. And now think about the lights around for holidays. When you put them up on your tree or outside, if one of those lights is bad or the wiring is bad in that one light, the whole string of lights is gone. It's gone. So because that stops electron flow. And when one area is stopped, the whole rest of the string of lights will stop as well. So remember we talked about it has to have the battery where the volts are provided, and this is a resistor. This black parts are resistors. And it'll do work here. The voltmeter measures the voltage, and then we have the switch to turn it on or off. All right, what we can do is we can now drag these into the different locations. Put the ammeter, put the battery, the switch, and we'll put our 3 resistors. So notice that the squiggly lines were for the resistors. The A was for the ammeter. The open, looks like kind of like an open door, is for the switch. And then this is for the battery. Now, parallel circuit is different. Parallel circuit is when we're going to have multiple ways of producing the electricity. It's not, so if one burns out, it'll just go a different route to be able to make it go. So we have the voltmeter for V, and we know the squiggly lines are for the resistors, and then the lines here are for our battery. And this is what a parallel circuit looks like. Let's say if it gets broken, that's okay. It can go through and go around here. So even if it's a broken circuit, it's all right. It will work just the same. All right, let's practice. Is this a series circuit or a parallel circuit? This one's a little bit of both. All right, now you've had great examples of what the parallel circuits and series circuits look like. And we know we have many examples of electrical circuits around us everywhere we are. Now you're going to do is build your own circuit. You're going to answer the questions in part 1 through 4, answer those, and then you're going to design your own circuit. Your circuit must contain all required parts. So it has to have a path, it has to have resistor, it has to have voltage like a battery, and it has to do something that's going to produce work like a light bulb. Make sure it is properly constructed and will work. If it's not going to work, you don't get the full credit for it. That's 5 points off if it won't work. Remember, the path must go from negative end of the battery to positive end of the battery, all the way around. And then we also have some questions on the bottom, 5 questions on your circuit. So draw a circuit or make a circuit, as well as answer the 5 analysis questions and the 4 in part 1. Looking forward to seeing your awesome work.